We've been talking about systems of differential equations for a while now. Time for a recap. So what are systems of differential equations? It's when you have multiple equations involving derivatives. Why do we care? That's a great question. We care about systems of differential equations because we care about how things interact. Now, a differential equation, the reason we study those is we say, how are things changing? But multiple things can be changing at the same time, and they can influence each other. This can happen in a variety of ways. For instance, one can be, take some springs, several springs linked together, and then say, okay, well, what's happening with their motion? Now, that's a really fun and interesting problem, but that tends to get into a system of equations, which can get very complicated and get a lot of equations very quickly. We want to keep things very simple now, because we're just beginning, right? We're beginners at heart. And so we want to channel our inner beginner. So we're going to do mixing. That's going to be our focus. And mixing is a really nice way to illustrate what's going on, because we can set things up relatively quickly and get a system of differential equations that we can be happy with. So what do I mean by mixing? Well, let's make up a simple problem. What we have is some tanks. And usually we phrase this in terms of brine, but it doesn't have to be brine. It can be anything at all. I've also put things like sugar, in case some people are like, man, these problems, they make me feel salty. Well, that's all right. Now we'll turn the sugar. Now they'll make you feel sweet. All right, so you have two tanks. Now, what's important here is the system of equations is when we get interaction between the two tanks. In other words, maybe we have some flows happening. And okay, that can be certainly a possibility. Which, in other words, we're flowing from one tank to another. And all right. But of course, there's also other things going on. We have things coming into our system, and they can come in on either side. And we have things exiting our system, and again, they can exit on either side. So how does this work? Well, we can just make up some numbers really quickly, and oftentimes it's easiest to see what's going on by actually doing an example. So I'll be very dangerous here and make up numbers. So let's say that this has 24 gallons. This has 20 gallons. This will come in at, say, let's do 2 gallons per minute. And when we talk about brine problems, it has to be salty, right? So what's coming in has to have some amount of salt. Well, okay, let's say it has, so this is 5 ounces per gallon. And then over here on this side, we'll have 6 gallons per minute. Oh, that's a lot more coming in on this side. That's all right. And not very salty here. It's 1 ounces per gallon. Now, notice that we have 8 coming in. Well, so we should have 8 leaving. Let's just split the difference. We'll have 4 gallons per minute leaving here and 4 gallons per minute leaving here. Now, you notice no concentrations down there because, well, it depends. The concentration changes. That's one of our goals. Now, in between the two, well, okay, what we should do is make sure we have some sort of balance. So notice how we had 8 in, 8 out, and that's for the system as a whole. Well, all right, so let's make up a little bit here. We have, okay, let's say we put, what's the number we haven't played with here? Let's do 4, well, we've done 4. All right, we'll do 4 again, 4 gallons per minute in. Now, at this point, I want to be careful. What do we see? Well, we have 6 coming in, so we should have 6 leaving. So we'll put 2 gallons per minute leaving. All right, okay, well, nice enough numbers. Now, what do we do? Well, when we're trying to model, we say, okay, we make up equations and variables. Let's have x1. This is the amount of salt in tank 1. And this is x2, which is the amount of salt in tank 2. All right, great. Now, what do we do? Well, from here we say, all right, how are things changing? Now the nice thing is we can talk about change locally, right? What's the change here? What's the change there? And that's oftentimes how calculus works. Think locally, solve globally. So how do things change? Well, we look at x1 prime, and that's, well, into tank 1, and then we subtract out of tank 1. Well, what comes in? Well, we have this flow in. There's 2 gallons per minute, 5 ounces per gallon. So that's coming in. That's increasing, so plus 10 coming in here. What else is coming in? We have something coming from tank 2. Okay, how much is coming from tank 2? Well, we have 4 gallons per minute, but now that's a flow rate. How do we go from flow rate to salt? Well, we have a nice little formula that says take your flow rate and multiply by concentration, and you're good to go. So here we have our flow rate is 4, and our concentration is x2 over 20. Subtract what leaves. We have 4 gallons there, 2 gallons there, so that's 6 gallons are leaving. So 6 is our flow rate, our concentration, x1 over 24. All right, and in a similar way, x2 prime into tank 2, subtract out of tank 2. Well, what happens here? Well, certainly we have from the outside source, we have 6 times 1, great. Then we have things coming from tank 1. Well, it's 2 gallons per minute. Then the concentration is x1 over 24, right? So x1 is the amount of salt, 24 is the number of gallons, x1 over 24. And by the way, we made sure our inflow equals outflow. That says that the water level isn't going up or down. Or we could say the brine level isn't going up or down. And finally, well, what's leaving? We have 4 here, 4 there, that's 8. So we're going to subtract 8, x2 over 20. And that's our setup. We can, of course, make it look pretty. Sure, why not? Everybody likes a pretty problem. So you get things like x1 prime. Well, let's put the x1 in front, 6 over 24 minus 1/4 x1. Here it'd be 1/5 x2 and a plus 10. And in a similar way, x2 prime, 2 over 24, 1/12 x1, 8 over 20. Well, we can get a 4 out of that. So that's 2/5 x2 and plus 6. And there we go. Now we have our setup. And then, of course, you say, well, can you solve it? Sure, with the right tools. And so that's one of the things we're going to talk about is how to solve problems like this. All right, well, let's keep moving along. Now, as we go and set up our systems of equations, we start to discover that could be the scenario where we have lots of equations, but not very many derivatives, or we can have few equations, but lots of derivatives. We can actually even go in between the two. There's this trade-off that happens. So how does one go between the two scenarios? Well, suppose we want to have more equations, but less order. Now, when I talk about less order, I'm not talking like chaos. We don't want crazy people running out on the streets saying, the arctangent is coming, the arctangent is coming. What we mean by saying less order is to say, oh, the derivatives involved are simple. They're like first derivatives. And the way to do that is you introduce sort of intermediate functions, which represents the intermediate derivatives. And that gives you a way to turn your system into more equations, yes, but fewer derivatives, which is great. In fact, it's sort of a preferred thing because it turns out that oftentimes what you can do is turn your problem into a big matrix. And computers love big matrices. But can we go the other way, which is to say, look, I want few equations. Maybe I just want one equation, because we're really good at that. That's what we spent the first few weeks mastering, one differential equation. Can we get to that? But of course, we have to pay a price. There may be a lot of derivatives involved. The answer is yes. Yes, we can. And for this one, there's something called the denotation. What is d? D is for derivative. So if I want to take the fourth derivative, I can say, well, that's the same as multiplying by d 4 times. So every time you multiply it by a d, that's a derivative. Then what happens is you can say, oh, I can rewrite my system of equations using this denotation. And now you can do elimination. Now there's ways to do elimination by hand, but there's also ways to do it in an automated fashion. So we can, again, make up a simple problem. So we'll keep it, like I said, very simple for right now. Suppose we have like x prime plus 2x plus y prime minus 3y is equal to, oh, we'll say t, and then x double prime plus y double prime equals t squared. All right, suppose we had that. Okay, what do we do? What do we do? Well, what we can do is we say, look, first, rewrite this using our notation with d. So what does that give us? Well, it gives us the following. It says, look, x prime, that's d times x. So we get d and then plus 2x. Here, it would be d minus 3y. Downstairs, d squared x. Here, d squared y. All right, now what do we get? Well, now that we have this expression, we can start playing around with things. We say, well, okay, so this says as matrix, d plus 2, d squared, d minus 3, d squared, xy equals t squared. And suppose we want to get an expression for just x. Well, Kramer's rule says what? Take the determinant of the coefficients. All right, we can do that. X. And then equals, now here, if you're solving for x, we're going to use this function on the right-hand side, replace the x column, right? This is the x column, the coefficients with the x. T squared, d minus 3, d squared. Well, this is 2 by 2 determinants, which hopefully we're going to get really good at because we're going to do a lot of them. And so you do want to be good at those. X, or on this side we'd have d squared times t, subtract d minus 3 t squared. Well, all right, what do we get? We get d cubed, then we're going to subtract d cubed. 0. Well, that's convenient. Here we'll have 2d squared, and we're going to add 3d squared. So we get 5d squared times x. Well, that sounds like something we might have a chance at. Equals what? Well, what's the second derivative of t? 0, right? Because first derivative is 1, second derivative is 0. Now, we'll have derivative of t squared is 2t. Don't forget the minus. And then minus times minus makes a plus, 3t squared. And d squared is double prime. So 5x double prime equals minus 2t plus 3t squared. And off we go. We probably could actually solve that one. But you know, the important thing is the process. All right, so this is good. This is great. This helps us find our sweet spot. So as we're working with these problems, we often find we're going to be in matrices. So let's remind ourselves of a few simple things. How do we work with matrices? There's a couple of things to know. One is, how do you take determinants? And we're going to focus, by the way, on 2 by 2s because that captures a lot of the basic ideas, and oftentimes it's enough of a workout for us. So determinants, remember, you have your diagonals. So down, AD, other diagonal, subtract BC. Great. How about multiplication? Well, you have to remember how multiplication works, and you might see a multiplication. You have to go along the rows in the first one, down a column in the second one. So this would give you the first row, second column, first row, second column, and then you do multiplication term by term, right? AF and BH. That's where you get AF plus BH. You do that over and over, and always, and you get your answer. How about inverses? Yes, we can do inverses. So if I want the inverse of a 2 by 2, 1 over the determinant. See, same expression. And then what happens is on the diagonal, you swap places. Off the diagonal, you leave them where they are, but you change their sign. And done. That's it. Now you might say, well, I'm a little bit worried. Did I do the inverse right? Well, you can check. Because what does it mean to be an inverse? Well, it means if you multiply the matrix times its inverse, you should get 1. Well, 1 here stands for the identity matrix. It's a matrix 1, 0, 0, 1. All right, and so you can always check your work. Indeed, it's one of the best pieces of advice, which is to say, check your work. It's simple to make a mistake, and indeed, the biggest thing that happens are copying errors. And so, be slow, make sure you haven't missed a thing. A simple minus sign, it will snowball and make things terrible for you down the road. So take your time, check your work. The other big idea, and we're going to do a lot with, are eigenvalues, eigenvectors. Now the way you find eigenvalues is you take a determinant, that's what the straight lines mean, of your matrix, subtract lambda on the diagonal. Sometimes we call this A minus lambda I, and you set it equal to 0. And now you solve. You say, okay, what can you get? Well, a couple possibilities, and each one is very interesting. We'll talk about what happens with our different possibilities. You can check if you have the right answer. The sum of the eigenvalues is the sum of diagonals. So in other words, if you have a matrix and you have your matrix A is A, B, C, D, well, you say, okay, what does A plus D equal? That should equal the sum of the eigenvalues. So A plus D equals lambda 1 plus lambda 2. On the other hand, if you take the determinant, that's AD minus BC, that's lambda 1 times lambda 2. And oftentimes, just this, you can figure out what your eigenvalues are. But it's still useful to go through the process just to be sure. How about eigenvectors? Well, when we're doing eigenvectors, we're looking for something where what? Now, here, the key is down here. An eigenvalue eigenvector pair is something where A, matrix A, times a vector V, is a multiple of the vector V. And so it's like, oh, it's the same vector to scale. The same vector, that's where you get eigenvector. So, how do you find it? Well, you start with your matrix A minus lambda I, and you say, all right, I need to find something, so I get out 0, 0. And oftentimes you can just stare at it and say, aha, I see something. If you can't, well, you can do the following. You can take a row and write it backwards. Flip one of the signs, and you're done. Now, check, right? Double check, like, okay, does that give 0? Does that give 0? If one of them gets 0 and one of them doesn't, mistakes were made. And that means maybe your eigenvalue is wrong, or you took A minus lambda I wrong. Again, catch mistakes early. The earlier you catch your mistakes, the better off you're going to be. So let's now talk about our basic ideas of linear systems. A lot of the terms we use match with what we talked about before. Things like Wronskian and homogeneous, linear independence, superposition. So the ideas are going to be familiar. one of the first things to remember is, how do you verify a solution? Well, verify is really a simple idea. Plug it in and see, does it match? And if the answer is yes, we're like, yeah, verified. And if it doesn't, we're like, no, not verified. Of course, obviously, if something should be verified and it doesn't work, probably mistakes were made on our part, though potentially, of course, a mistake was made by the person who wrote the problem. But verify is more than just saying, hey, this actually works. Verify also comes into the idea of saying, well, I have a solution almost, I just need to tweak it. Maybe I have to get the right constants involved. And the way to figure out the constants is you plug it in. And so the idea of verifying can actually be a pretty useful and powerful tool. Now, another tool that we have, we don't use it very often, but it's good to have, is the Wronskian. Now, the goal of the Wronskian says, look, where the Wronskian is non-zero, life is wonderful. We get uniqueness, and we're just like, we love that. Where the Wronskian is zero, it's like things break down, we don't know, maybe we can solve it, maybe we can't, uniqueness gets tossed out the window, so forth and so on. Now, how do you actually compute the Wronskian? Well, if you have solutions, what you do is you form the columns of a matrix with your solutions, and then take the determinant. A few more things is superposition, which says, oh, if I have some solutions and I'm homogeneous, now what do we mean by homogeneous? Well, that's if we have something in the form x prime equals a of t x. So this is homogeneous, and it's linear. So if we have solutions, then what we can do is we can make more solutions. And it's wonderful. You take a linear combination. Now, this will be what we call the general form. So in other words, if you have two which are linearly independent, which you can check with the Wronskian, then all solutions would look like this for a 2x2 system. Now, you say, okay, general form, all solutions. What if we want the one solution? Well, for that, there's usually an initial value. And what do? Well, we plug in, right? So we have that x is ax1 plus bx2. So we say, oh, well, that says x of 0 is ax1 of 0 plus bx2 of 0. And here, this is a system of equations for a and b. But it's a nice system. It's the kind of system that we're used to, like two equations, two unknowns, and we go ahead, solve for a and b, and that gives us our desired solution. And then we say, great, now we have the solution that we're after. And so you say, okay, make sure you know what you're looking for. There's actually sort of three things that you will look for. General form, a specific solution for initial value, and then the last thing deals with fundamental matrix. So let's talk about that. What's the fundamental matrix? Well, you'll see the word fundamental, and that just says, you know, this matrix is somehow capturing the solutions. And the way you do it is you say, okay, we'll take the solutions and capture them in a matrix. So we call it phi of t, and the columns of phi are our solutions. See how they've been captured? Now, fundamental matrices are not unique. However, there is a best one. And the best fundamental matrix is called e to the at. And it really does behave like an exponential function. What you would expect for properties of an exponential function, e to the at has. And how do you find it? Well, if you have a fundamental matrix for x prime equals ax, and so we want to be really careful here. So x prime equals ax, not x prime equals a of tx. No, that's out. We don't want that. We want just a, constants. So then e to the at, that's phi of t, phi 0 inverse. And now that's the best. Why is it the best? Because it has this really awesome property. Namely, if you have x prime equals ax, with initial condition x of 0 given, then you say, this says our solution should look like e to the at x 0. So if you can compute e to the at, life is good. Life is wonderful. And indeed, there are ways to do that. There's shortcuts. So one shortcut, if you have repeated eigenvalues, then e to the at is e to the lambda t, I plus t, a minus lambda I. There's another one which says, well, what if your eigenvalues are complex? So lambda equals alpha plus minus beta I. Well, in that case, you get that e to the at looks like the following, namely e to the alpha t cosine beta t times the identity matrix plus 1 over beta e to the alpha t sine beta t times it is a minus alpha I. And so, again, we have ways to compute e to the at. And once you have that, you've got a couple things really quick. One, you have an initial value problem, you quickly pound out e to the at, you multiply x0, life is good, you're done. What if you want general form? No problem. Why? E to the at is a fundamental matrix. It's the best, but it's one of them. So you say, great, grab the columns, column, and you grab the columns of e to the at, then you've got x1 and x2. And now you say, great, constant x1 plus constant x2, general form. And so use your tools. Using the tools of computing e to the at makes life a lot more fun because it makes things a little bit more straightforward. And we kind of like it when that happens. I kind of do. All right. So this has a lot of information here. You kind of almost couldn't squeeze it all in, but let's just remind ourselves what we have. We want to use an eigenvalue method for solving a system. So what does that mean? Well, either we have a system given to us, x prime equals matrix x, where these are numbers, or we may have it written this way, x prime equals ax plus by, y prime equals cx plus dy. So know how to go from a system to, a system of equations to a matrix form. And if you do go this way at the start, remember at the end, you've got to go backwards. And going backwards is pretty easy. You just say, okay, read off the entries. So what do you do? What do you do? Well, it turns out there's basically a few things you do. The first thing, always, when you have a matrix involved. So if you see a matrix with numbers, you're like, I'm doing eigenvalues. Yes, you are. You've got to compute the eigenvalues of the matrix. And then depending upon what happens, you say, okay, I've got 3 possibilities. The first possibility is that my eigenvalues are distinct real numbers. If that's your case, and depending upon what you do, normally the next thing you have to do is say, find those eigenvectors. And once you have those eigenvectors, E eigenvalue t eigenvector, E eigenvalue t eigenvector, you have 2 solutions. From there, you can do all sorts of things, and life is good. If you have repeated eigenvectors, well, compute e to the at using the shortcut. And then that's the fast way. Now, the longer way to do this is to do what? Well, for repeat, what you can also do is you can say, look, you want to find a minus lambda I times v equals 0, and a minus lambda I times w equals v. And once you have found that, then your first solution is e lambda t v, and your second solution is e lambda t bump up. Well, you wait, that won't work. That's why we found the w to say, aha, there's a small correction. And now you have your 2 solutions. But in practice, if we're timed, it's faster to compute e to lambda t. The last scenario, complex. Now, if you have complex, you can, of course, do the following. Find an eigenvector and break it apart. Real plus I times the imaginary parts, right? Just like we do with numbers, we can do with vectors. And that's the eigenvector for the eigenvalue alpha plus beta I. So what do we have? Well, we have E eigenvalue t, using properties of e to a complex number. So, right, just like we have E eigenvalue t, here's E eigenvalue t. Eigenvector, eigenvector. And now we say, great, FOIL this out. Take the real parts, take the imaginary parts. Those are solutions, because the solutions come in conjugate pairs. Now, this works. In practice, it can become very lengthy. So, again, if you have the formula, a better approach, or maybe I should say a faster approach, is to compute our e to the at. And that uses the formula we talked about a few minutes ago. Say, okay, now if you have that, you can say, if I have e to the at, I can grab my columns. There's x1, x2. Life is good. Things go quickly. So that's the three scenarios you might find yourself in. Distinct real, repeated, complex. There's three things you might be asked to do, which we mentioned before. General solutions, fundamental matrix, or e to the at, and specific solutions with initial values. And so make sure you know how to handle each one. Make sure you know what the answer to each one should look like. And of course, when you're reading a problem, it's always good to answer the question and stop there. Don't answer things that weren't asked. That's taking time away from other equally fun problems. Now, the last thing to talk about, non-homogeneous or non-homogeneous. Now, this means that there's something here, this f of t on the end. So if it wasn't there, homogeneous, non-homogeneous, homogeneous, non-homogeneous. So it's as simple as, is there something there? Now, if there is, we do what we did before, which is to say, okay, I'm going to think about breaking the problem into two parts. One part is to say I have my complementary solution, xc, and one is my particular solution, xp. Now, for xc, say that f of t goes away. You solve that problem. Now, the xc is used to say I can always get my initial conditions. All right, so let's say we're comfortable doing xc. That's eigenvalue techniques. We're really good at that. How do we find xp? Two options. The first option, undetermined coefficients. And you'll notice it says preferred. Why? Well, because it's more or less straightforward. The process will follow a very predictable path. And it's the making a list. You're making a list, checking it twice, gonna find out which functions are nice to include in the particular solution. You start by saying, I need to seed the list. You split up your function. And you say, okay, grab the pieces of it, and all right, now that's the seed of your list. You go through and you say, I need to check a couple things. Do I have any powers of t? If I do, make sure I have all lower powers of t. Are there any sines or cosines? Make sure they come in pairs. 2 by 2, right? Just like into the arc. 2 by 2. Do I overlap with any of the functions showing up in xc? If there are things which overlap, you need to add some additional pieces so that you can say, look, I won't have anything vanishing on me. So be careful, be careful. So it's one of those things where it's a little bit different than before, where bump is like, just take it, move everything up. This says, no, don't move everything up, just like add onto. All right, now that you have your list, it's been populated, you say, all right, now my XP says First function on my list times an unknown vector. Second function on my list, unknown vector. Third function on my list, unknown vector. Dot, 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 dot. And I say, all right, now I know what xp looks like. Other than these vectors, I don't know. But now I plug it in to the differential equation, and running like I would verify, I say, well, what happens? What would I need to set those vectors in order for things to work out? And so that's the feeding, and then you solve. It sounds like a lengthy process. In practice, it goes relatively quickly. The only thing that might take a bit of time is the part where you have to solve, because you'll get a system of equations. So just be careful. Now, the thing is, undetermined coefficients, one of the things is it's preferred, but not always available. So the thing here is that in order to use this, f of t must be, and this is a technical term, nice, which is to say, what kind of things can f of t look like? T to a power, exponential, sines, cosines. That's it. If it doesn't look like that, out of luck. That's all right. That's why we have a second method. Okay, so variation of parameters. Now we call it variation of parameters. It will feel, the first time you see it, like, this feels more like we're doing linear first order. It kind of is. But it really does, when you think about what's happening. How does variation of parameters work? It says, well, you need to multiply your homogeneous pieces by some functions, and that'll give you your non-homogeneous part. E to the at, that's your homogeneous solutions. And you're saying multiply it by some function, and that gives you your particular solution. So it does fall into the, oh yeah, it's the same mindset as variation of parameters. Now, what's nice about variation of parameters is it's more flexible. Variation of parameters will work when undetermined coefficients will work, but not vice versa. So variation of parameters handles more cases. But if you have a choice between the two, I encourage you, stick with undetermined coefficients. In some sense, the reason why undetermined coefficients is a little bit easier to work with is it avoids calculus, and it's a little bit less computational intensive. Now you can see that the avoid calculus is there's no integral in undetermined coefficients. The computational intensive is you have to multiply by matrices. Multiplying by matrices takes time. We want to avoid that because oftentimes we might have not a lot of time. All right, so how does it work? There's a formula. The particular solution, e to the at integral e to the minus at f of t dt. Surprisingly, if you were to solve x prime equals ax plus f of t, where these are not vectors or matrices, just normal things, you'd get the same formula except little a's, and you say, wow, we worked all this time to go from little a's to big A's? Yes. Yes, we did. And life was good. Now, when we're solving for the particular solution, you can choose your constants to be anything. I encourage you to choose constants to be 0. You'll notice here, e to the minus at. We've talked about how you find e to the at. To find e to the minus at, don't start over from scratch. Instead, just say, look, I have e to the at. Now, everywhere you see a t, put a minus t, and life is good. Life is good. And that brings us to the end. So, good. We've learned a lot, and hopefully we're practiced. We're ready. Eigenvalues, wonderful things. And if you like them, you'll see them again. And if you don't like them, you'll still see them again, because they show up in a lot of places. It's been fun learning about systems. Don't worry, we still have more things to learn about, and we'll be doing that very soon. See you then. Bye.